Hello everyone, welcome to joining me at the Microsoft Research Summit 2021. I'm Shangtong Zhang from University of Oxford. Today I'm going to present our work breaking the deadly child with a target network. Let's get started by briefly introducing the deadly child. So the deadly child is a fundamental theoretical challenge in reinforcement learning. Basically, there are three very important techniques in reinforcement learning: off-policy learning, function approximation, and bootstrapping. In off-policy learning, we have two policies. The first one is behavior policy mu, and the second one is the target policy pi. The behavior policy mu is used for interaction with the environment for data collection, and the target policy pi is the policy that we are actually interested in. With function approximation, we are able to represent quantities of interest with parameterized functions. We can use either linear parameterization or nonlinear parameterization. But in this talk, I will focus on linear parameterization. With bootstrapping, we compute the updated target for our parameterized function by using the parameterized function itself. For example, let's say we have a parameterized function f with parameterized by w. Then we compute the updated target for f by using another function gw. So in this way, we kind of achieve some recursive update. All the three techniques are very important and successful in reinforcement learning, but unfortunately, if we try to combine all the three techniques together in a single reinforcement learning algorithm, unfortunately, the resulting algorithm is very likely to diverge, so it won't behave well. This is a well-known deadly child issue. One thing to note is that when we talk about the deadly child issue, we consider only algorithms that are computationally efficient. In other words, algorithms that have linear computational complexity with respect to the number of input features. If we remove this constraint, there are indeed many other algorithms, for example, least square algorithms, but they are very computationally inefficient. There are actually existing solutions for the deadly child issue. Basically, there are two kinds of algorithms: gradient TD methods and emphatic TD methods. Both algorithms are very successful from the theoretical side, but the problem is they are not appreciated by practitioners. So in deep reinforcement learning practice, there haven't been very successful application of gradient TD and emphatic TD. Instead, practitioners in deep reinforcement learning use target network to empirically stabilize off-policy reinforcement learning algorithm. So recall in bootstrapping, we try to fit our function fxw to a target gw computed by the parameter itself w. If we consider bootstrapping with a target network, instead of using gw, we use g theta as the updated target. So here theta is a copy of the parameter w, and is updated slowly to track the main network w. So in this way, we are able to make sure that the updated target g theta changes very slowly. So the intuition behind the target network is that it works because it provides a stabilized bootstrapping target. And in practice, target network is very successful. It's used in DQN, DDPG, TD3, and SEC. So given the empirical success of target network in deep reinforcement learning, so the central question we want to answer in this talk is that can we make any theoretical statements about the target network and the deadly child? Can we prove that target network is actually a useful tool for breaking the deadly child? The answer is yes. Let's start with some motivating example. So here we consider Bear's counterexample, which is a very famous example to demonstrate the deadly child, and we consider linear Q-learning, which is also very standard. So this is the updated rule for linear Q-learning. So W is our weight parameter, and X is our feature matrix. If we run linear Q-learning in Bear's counterexample, it's well known that it will diverge as shown in this plot. Within very few first steps, the error goes to infinity, so the weight vector W diverges. But surprisingly, if we combine linear Q-learning with the target network, then in Baird's counterexample, it converges well. So we did nothing fancy. We just add a target network theta here. So this is the updated rule for linear Q-learning with the target network. So if you compare this rule with the previous update, you can see there is only one difference. When computing the updated target for the max operator, we use theta t instead of wt to compute the value. So here theta t is the target network, and we update the target network gradually towards wt. And there are, of course, two learning rates, alpha and beta. We make sure that alpha is sufficiently large than beta, so the target network changes very slowly. So there is really nothing fancy. We just add a target network. But as shown by the blue curve, linear Q-learning with the target network converges very well consistently. So this curve is averaged over 30 independent runs, so it's very reliable. So do you think it's by accident? Our answer is no. We actually prove that target network is an effective method to break the deadly child in linear reinforcement learning. To be more specific, we analyze this updated rule for linear Q-learning with target network. This is a variant of the previous update. There are two main differences. The first one is we introduce a ridge regulation term weighted by eta in the update to the main network W. The second difference is in the target network update to theta t, we added two projections, so tau b1 and tau b2. Those two projections are projection to balls of radius bi. So in practice, we can set the radius of the balls to be a large value, so it rarely take effects. We find if the norm of the feature matrix X is not too large, and the balls B1 and B2 used for computing the projection are not too small, then we prove that the weight vector W generated by the linear Q-learning with the target network converges almost surely to regularize the TD fixed point. So I think this is a very important result, because without target network, we can say the linear Q-learning just diverges. But by using two projections and using the ridge regulation, we can make sure that the iterates generated by linear Q-learning converges. So one important thing to note is that here both the ridge regulation and the projection are all sufficient. They are not necessarily necessary. You can see in previous example, we don't have projection, we don't have ridge regulation, but the algorithm still converges well. So a possible future work is to design a sufficient and necessary condition. But here we focus on the sufficient condition to use the ridge regulation and the projection. Another important thing to note is that here the behavior policy can be W dependent, so it can change every time step, and it can be very different from the target policy. Both features are appreciated by practitioners. You may wonder, why do we need two projections in updating the target network? So if you are familiar with optimization literature, we usually have only one projection, but here we have two projections, tau b1 and tau b2. If we have only one projection, tau b1, we will get some ODE like this to analyze the asymptotic behavior of the target network update. So in this ODE, there is a reflection term, zeta t. So because of this reflection term zeta t, it's very difficult to analyze the asymptotic behavior of the target policy. But we are able to remove this reflection term zeta t with two projections, tau b1 and tau b2. So with those two projections, we get a very nice ODE, and we are able to analyze the asymptotic behavior of the target policy. Also, the second projection, tau b1, also ensures the target network changes sufficiently slowly, so our two-time scale setting will hold. In this talk, we consider linear Q-learning as an example to use our analysis of target network. Actually, our analysis is widely applicable. It can be used in both policy evaluation setting and control setting for both discounted MDPs and average reward MDPs. If you are interested in more details, please check out our paper at arXiv. Finally, I want to thank my collaborator Hengshui Yao and Simon Whitesong. Here are some references, and thanks for joining the talk.